Hello children, welcome to online classes. We will now discuss the properties of p block elements and their compounds. We are now discussing the properties of p block elements and their compounds. Let us see the meaning of p block elements first. The elements in which differentiating electron enters p subshell of the outermost shell are called p block elements. That is, elements in which differentiating electron enters into p subshell of outermost orbit are called p block elements. The elements of the groups 13th to 18th group are called p block elements. 13th to 18th belong to p block. In first year, we have learned 13th and 14th groups. In first year, we have seen the properties of 13th and then 14th group elements. In second year, we are going to learn the properties of remaining groups. That is 15th group, 16th group, 17th group and 18th group we are going to see. In second year, we are going to learn the properties of 15, 16, 17 and 18th group. Today we are going to discuss the properties of 15th group elements. Now let us see what we are going to cover in 15th group elements. General properties of 15th group elements. Nitrogen preparation and properties, means preparation of nitrogen and its properties, preparation and properties of ammonia, oxides of nitrogen and nitric acid, phosphorus and compounds of phosphorus. So we are going to discuss general properties of 15th group elements, nitrogen preparation and its properties, preparation and properties of ammonia, oxides of nitrogen and nitric acid, phosphorus and compounds of phosphorus. Now in today's lecture, we are going to cover electronic configuration of 15th group elements, physical and chemical properties of 15th group elements, anomalous properties of nitrogen, hydrides of 15th group elements, preparation and properties of nitrogen gas. So we are going to see the configuration of 15th group elements, physical and chemical properties of 15th group elements, anomalous properties of nitrogen, hydrides of 15th group elements and preparation and properties of nitrogen gas. Now coming towards 15th group elements. The 15th group includes nitrogen, phosphorus, arsenic, antimony and bismuth. 15th group includes nitrogen, phosphorus, arsenic, antimony and bismuth. The group 15 is also known as nitrogen group. It's starting with nitrogen, so it's called nitrogen group. The elements of 15th group are also known as nicogens. They're also known as nicogens. The term nicogen is derived from the ancient Greek word meaning choking or suffocating. As hydrides are poisonous and cause choking, they are called nicogens. Hydrides are poisonous and they cause choking, hence these elements are called nicogens. So the term nicogen is derived from the ancient Greek word which means choking or suffocating. As hydrides are poisonous and cause choking, these elements are called nicogens. Now the properties which we are going to discuss are electronic configuration, atomic radii, ionization enthalpy, electronegativity, oxidation state and covalency, means maximum number of covalent bonds which are being formed. So configuration, atomic radii, ionization enthalpy, electronegativity, oxidation states and covalency. Let us see first the electronic configuration. So they have a general configuration of ns2np3. ns2np3, 15th group elements have 5 valence electrons and configuration is ns2np3. The first element nitrogen is 2s2 2p3 we have, means it will be 7, so it will be 1s2, it is 2s2 and then 2p3 we have. Altogether 7 electrons are there, of which 5 of them are valence electrons. Similarly, next one will be 3s2 3p3, then comes 4s2 4p3, then we have 5s2 5p3 and finally we have 6s2 6p3. So their general configuration will be ns2 np3 we have, nitrogen being 2s2 2p3. Now let us see how the atomic radii changes now. So radius varies. As we go down the group, atomic radii, ionic radii will be increasing. But one point to understand is the increase is not uniform throughout. It increases, but increase is not uniform throughout. What we can see is from nitrogen to phosphorus, we can see more increase of size. We can see more increase can be seen from nitrogen to phosphorus. And from phosphorus to arsenic, we can see only less increase of size can be seen from phosphorus to nitrogen. Less increase. Increase is there, we have lesser increase. That is because in arsenic, we have 3d electrons are there. If you go back, we can see once again, arsenic is having 3d10 now. So in arsenic has 3d electrons. And we know that 3d electrons cannot screen the nuclear charge effectively. And thereby, arsenic is going to have more nuclear charge. And so, we have only lesser increment of size from phosphorus to arsenic we have. So, arsenic has 3d electrons. Arsenic is having 3d electrons in that. And 3d electrons cannot screen the nuclear charge. Thereby, arsenic has more nuclear charge. Hence, we cannot see much size increment from phosphorus to nitrogen. And arsenic and antimony both have same d electrons only. And when it again comes to say antimony to bismuth, again we have further lesser increase of size can be seen here now. Again we can see lesser increase of size. In bismuth again we have F electrons are present. If you see bismuth here, we have F electrons are there. F electrons also cannot screen the nuclear charge much. Once again, bismuth has more nuclear charge and thereby we cannot see much increase of size from antimony to bismuth we have. So when you see final conclusion, from nitrogen to phosphorus, we can see more increase. From phosphorus to arsenic, we can see lesser increase. Arsenic is having d electrons there. And from As to Sb, both have d electrons only. We can see relatively normal increase can be seen. And then from Sb to Bi, again we can see lesser increase because bismuth is having their F electrons and F electrons cannot screen nuclear charge. They have more nuclear charge. Now we can see finally like this. From arsenic to bismuth finally is only a small increase in the radii due to ineffective shielding of completely filled d electrons and F electrons respectively we have. So arsenic has lesser increase. Bismuth also has lesser increase because of completely filled d electrons in the case of arsenic and F electrons in the case of bismuth we have. But atomic radii will be increasing down the group. So nitrogen being smaller size, bismuth being the larger size we have. So nitrogen lesser than phosphorus, lesser than arsenic, lesser than antimony, lesser than bismuth we have. Atomic radii is increasing down the group. Now next property is ionization enthalpy we have. Now the ionization enthalpy of 15th group elements is higher than 14th group elements. It is because of half-filled p sublevel. So they are having NS2 NP3. They have NS2 NP3 configuration. They are having P3. P3 is half-filled sublevel. So thereby they are having more IP values when compared to 14th group also now because of half-filled sublevel. However, down the group again, as atomic size is increasing down the group, we can see decrease of ionization enthalpy. Since atomic size is increasing down the group, ionization enthalpy decreases down the group. Once again, we can observe one point here. The decrease is not going to be uniform. It's not going to be uniform. That is because reason is the size of these atoms is not increasing uniformly and therefore decrease of IP will not be uniform there. So IP will be decreasing, but decrease will not be uniform because the increase of atoms is not uniform in the case of 15th group elements. The order of IP values are nitrogen more than phosphorus, then arsenic, then antimony, then bismuth. Means the order is remaining same only, but the uniformity will not be there in that order. Then comes electronegativity. Electronegativity, normal trend only. It will be decreasing down the group with the increase of the atomic size we have. So nitrogen being the highest, bismuth being the least we have. But actually nitrogen is coming to a third highest element in the periodic table here. That is first one is fluorine is having 4 units of En value. Second element is oxygen. It is having 3.5 units we have. And next element is nitrogen. Nitrogen is having 3.0 units we have. So nitrogen is the third highest EN element in the periodic table. In the Pauling scale, we can see that. So IP values are decreasing down the group with the increase of atomic size. And then comes the non-metallic nature. The non-metallic nature depends upon the electronegativity. And just now we have seen EN values are decreasing down the group. And so we can see decrease of non-metallic nature and we can see increase of metallic nature. So the first two elements, the nitrogen and phosphorus, these two are non-metals, and the remaining two elements, AS and SB, are coming under metalloids. Last is coming under true metal we have. So down the group we can see that metallic nature is increasing and non-metallic properties decreasing. So nitrogen, phosphorus are non-metals, arsenic, antimony are metalloids, and bismuth is a metal we have. So down the group electronegativity is decreasing, thereby non-metallic properties decreasing, electropositivity is increasing, thereby metallic nature is increasing. So nitrogen and phosphorus are non-metals, AS and SB are metalloids, and Bi is a true metal we have. Then comes various oxidation states. See, once you see the configuration, that is say NaS2 and P3, from this we can see the oxidation states now. The common states are -3, +3 and +5 states we have now. They can share the 3 electrons. If they are sharing to more electropositive element, then they are going to get a negative charge now. More electropositive element. They are going to share with more electronegative element. They are going to get +3 charge. And they can share even 5 electrons also. Then they are going to get +5. So implies that the common states of 15th group elements are -3, +3 and then +5 states we have. Nitrogen exhibits -3 to +5 states. All states are there between -3 to +5 states. Because of smaller size and high electronegativity, it even goes to -3 state also. And down the group, because of inert pair effect, stability of +3 will be increasing. And then down the group, stability of +5 starts decreasing now. It implies that bismuth has a stable +3 state, we can say, and nitrogen has a stable +5 state, we can say now. So down the group, because of inert pair effect here, +3, stability of +3 is increasing, and +5 state stability starts decreasing. So the last element can be in +3 state and first element can be stable in +5 state we have. So therefore what happens is the oxidation states of nitrogen, say from +1 to +4, +1 to +4 disproportionate in acidic solutions easily now. That is because for nitrogen +5 is more stable. For bismuth +3 is more stable. So when you take a reaction like HNO2, that is the nitrous acid, the state is +3 here now. +3 state changes into here +5 state. So +3 easily changes into +5 state because all +1 to +4 states disproportionate in acidic solution. Similarly, in the case of phosphorus, nearly all intermediate oxidation states, they start disproportionating to +5 and -3 states in both alkali and then acidic medium. So in the case of nitrogen and phosphorus, we can see +5 state more stable. In the case of bismuth, we can see +3 state more stable. Let's take the example of phosphorus also. If you take an acid H3PO2, where you have here +1 state, and here it changes into H3PO4 and then PH3. This is upon heating takes place now. H3PO3 has a state of +5 here now. Here it is a -3 state for phosphorus we have. So +1 state is changing into +5 state and then -3 state we have. So therefore, even in the case of phosphorus also, the intermediate oxidation states disproportionate into +5 and then -3 state in both alkali as well as in the acidic medium. Now, however, +3 state, in the case of arsenic, antimony, bismuth, they are stable with respect to disproportionation. Implies that if arsenic, antimony, bismuth are there in +3 state, they will not undergo disproportionation because for them +3 state itself is stable state now. So only lower states of nitrogen and phosphorus will disproportionate. Next, covalency, maximum number of covalent bonds that they can form. The maximum covalency of nitrogen is 4. Means nitrogen can form to a maximum extent of 4 covalent bonds. Suppose when you see ammonium ion formation, if you are seeing NH4 plus here now. So nitrogen is forming altogether 4 covalent bonds here. 3 of them are normal covalent bonds. We can take like this. One is going to be a coordinate covalent bond with hydrogen we have. So therefore, it can form a maximum of 4 covalent bonds because of non-availability of vacant d orbitals. The elements like phosphorus, arsenic, they can show a covalency up to 6 because of the availability of the vacant d orbitals. So they can expand octet further. Means, for example, when you take say PCl5, can take up even Cl minus also and exists as a PCl6 minus it can form. Similarly, AS also can form AsCl6 minus. So this arsenic and then phosphorus, they can show a covalency up to 6 because of availability of the vacant d orbital. So nitrogen shows only 4. It can't expand further because of the non-availability of vacant d orbitals. Then comes anomalous properties of nitrogen. Nitrogen differs from the rest of the members because of small size, high electronegativity, high ionization enthalpy, and non-availability of d orbitals. This property remains same for every group. The first element of every group differs from the rest elements. Here also, nitrogen differs from the rest because of small size, high electronegativity, high ionization enthalpy, and non-availability of d orbitals. Nitrogen has a unique ability to form p-pi bonds with itself and with other elements also. That is, for the formation of p-pi bonds, size is very much important. Small sized atoms can form very easily multiple bonds. And nitrogen being smaller size, it can form very easily multiple bonds can be formed. So it forms a triple bond between two nitrogen atoms. Hence it exists as diatomic gas where the nitrogen forms two triple bonds there now. And nitrogen is chemically inert because of the high bond enthalpy of the triple bond there now. But when you take phosphorus there now, because of larger size, it cannot form p-pi multiple bonds. But so phosphorus exists as a different structure. It has it has tetrahedral structure like this, where you have phosphorus atoms here. Means in this structure P4, each phosphorus is forming 3 bonds, but all of them are single pp bonds only. And in this case, nitrogen can form multiple bonds, and again it requires 3 bonds only here. Phosphorus also forms 3 bonds. Nitrogen also forms 3 bonds. Because N is small size, it can form multiple bond with itself only. And because P is larger size, though it requires 3 bonds, it cannot form multiple bonds. Hence it forms 3 bonds with other 3 phosphorus atoms. Thereby phosphorus exists as P4 molecule and nitrogen exists as N2 molecule there. So tetrahedral structure is for P4 molecule. Then nitrogen single bond strength is less. Single bond strength is less when compared to PP single bond strength. That is, nitrogen is small size. Atom N is very small size we have. And so the non-bonding electron pairs come close in NN single bond. When you take NN single bond here, the atoms are very small size. Therefore, all non-bonding pairs, 1, 2, 3, 4, 5 here, 1, 2, 3, 4, 5. So these electrons come very much close to each other now. When these electrons come close to each other, they start repelling. Non-bonding pairs undergo more repulsions now. This repulsive force decreases the bond strength. Thereby, NN single bond strength is very much less. When it comes to PP single bond, phosphorus being larger sized atom, the non-bonding pairs will not come too close. Hence, in the case of PP bond here, these two are large sized atoms now. Though they also have same number of electrons as nitrogen has, because of larger size, electron pairs are very much far away from each other. Thereby, they won't experience much repulsions. Thereby, thereby the repulsions between non-bonding pairs is less. Hence, the bond strength is more. So, in the case of nitrogen, the repulsions are more. The repulsive force decreases the NN bond strength. In phosphorus, repulsions are less and thereby strength is more. So, finally, NN single bond strength is less when compared to PP single bond strength due to inter-electronic repulsions, that is of non-bonding pairs. Heavier elements of this group do not form p-pi p-pi. For the formation of p-pi p-pi bonding, essential requirement is small size. Only small sized atoms can form p-pi p-pi multiple bonds. Heavier elements are not smaller size, so therefore they cannot form p-pi p-pi bonds as their orbitals are larger in size and diffuse. They can form p-pi d-pi bonds, they can form. So nitrogen cannot form p-pi d-pi bonds, whereas other elements can form p-pi d-pi bonds. Summary is that nitrogen forms p-pi p-pi multiple bonds because of small size. Other elements cannot form p-pi p-pi bonds because of larger size, but they can form p-pi d-pi bonds. Nitrogen has a maximum covalency of 4 because of the absence of d orbitals. It's having a maximum covalency of 4 only because of absence of d orbitals there. With this, we have done with the general characters of the 15th group elements. Now, hydrates of 15th group elements. So, the general formula is MH3 and these hydrates are NH3, PS3, ASH3, SbH3 and BaH3. So, general formula is MH3 we have. Let us see the properties of these hydrates now. First of all molecules are covalent in nature. Covalent in nature. Then comes stability. Stability is decreasing down the group. See, when you say the molecules are covalent in nature, in covalent molecules, the stability depends upon the bond strength between metal here, depends upon the M and then H bond strength. This bond strength depends upon the extent of overlapping of the orbitals. Again, the overlapping depends upon the size of the atoms here now. So, size of the atoms down the group is increasing now. When you have a larger sized atom, overlapping will not be much. Means in the case of bismuth and hydrogen, we cannot see much overlapping. Means Bi and hydrogen has very less overlapping. We have more overlapping only in the case of nitrogen and then hydrogen. So therefore this bond is strong when compared to this bond here. So thereby we can see a decrease of stability down the group. So that is because of decrease in the bond strength of M and H bond strength is decreasing down the group. Reducing strength is increasing now. Why it is increasing means when the bond strength is decreasing here, it can break very much easily and give us hydrogen. That implies the reducing strength is increasing down the group. So reducing strength is actually depending upon the bond strength only. Since bond strength is decreasing, then we can see increase of reducing strength down the group. Then comes the basic nature. All these compounds are basic in nature because of the availability of electron pairs. So all of them are Lewis bases. So ammonia has a Lewis electron pair on that. Phosphine electron pair and so on and so forth. All have electron pairs. All of them are electron pair donors only. Therefore, all of them are coming under Lewis bases. But here, as the size of the central atom is gradually increasing here, electron density on the central atom gets reduced. So nitrogen is a smaller size with lone pair here. And then say phosphorus, let us take second element itself, is a larger size we have. Both have same lone pair only now. But here, larger size, electron pair availability of the pair gets reduced here now. The pair availability is very much more. So nitrogen can donate electron pair easily when compared to phosphorus. Hence, NH3 is a strong base when compared to PS3. So we can say that basic nature is decreasing down the group. So all are covalent molecules. Stability decreases because of decreasing in the bond strength. Reducing strength increases because of, once again, decrease of the bond strength. Basic nature decreases because of availability of electron pairs decreasing down the group. Next, regarding the boiling points. When you say all molecules are covalent in nature, so boiling points depends upon the van der Waals forces. And van der Waals forces depending upon the molar mass. So more molar mass we are going to get more van der Waals forces, more the boiling points we have. So bismuthine has a more molar mass. It is having a higher boiling point. The only exception comes ammonia. Exception is ammonia because ammonia is having a hydrogen bonding. It is exceptional when compared to van der Waals forces. Thereby ammonia comes in between now. So therefore highest boiling point is for bismuthine only and least boiling point is for phosphine we have. Ammonia is exception because of its hydrogen bond. So in the case of boiling points we need to see the molar mass. More the molar mass, more the van der Waals forces, more the van der Waals forces, more the boiling points we have. Exception is ammonia because of its hydrogen bond. Now, due to absence of intermolecular hydrogen bonding in pH3, pH3 has a low boiling point when compared to ammonia. pH3 is having low boiling point when compared to ammonia because of the absence of hydrogen bonding in that. Next, coming towards the shapes. All hydrates are pyramidal because of sp3 hybridization of the central atom here and the presence of lone pair of electrons are there on that. So actually if it's only sp3 without lone pairs, that is going to be perfect tetrahedral. Because you have a lone pair of electrons on that, the molecules are becoming pyramidal in structure. The bond angles decrease and reach 90 degrees because pure orbitals start involving in bonding down the group. So actually they are undergoing sp3 hybridization. So the molecules are pyramidal, they have one lone pair. But down the group bond angles are decreasing. They are reaching 90 degrees because down the group the pure orbitals involve in bond formation. So we can see the angles are slowly getting reduced here now. So ammonia is having 107 degrees. So you need to remember the bond angle in ammonia. So bond angles are getting reduced because down the group we can see pure p orbitals involving in bond formation. So up to here we have done hydrides. Next, oxides. Oxides of 15th group elements. 15th group elements form two types of oxides, trioxides M2O3 type and pentoxides M2O5 type we have. So two types are there, M2O3 and M2O5 we have two types here. These oxides show acidic, basic or even amphoteric property depending upon the nature of the element. Depending on the nature of the element, they are having acidic property, basic property and even amphoteric property also. In the case of trioxides here, the first two trioxides, their respective oxides, they are acidic in nature. And the next two elements are amphoteric and thereby their oxides, they are metalloids and thereby their oxides are coming under amphoteric in nature. Last is a true metal. Bismuth is a true metal and thereby its oxide is a basic in nature. Similarly, in the case of pentoxides also, the first two oxides of nitrogen and phosphorus, they are acidic in nature. Next two amphoteric in nature. Last is bismuth. That is a basic in nature we have. So therefore, down the group we can understand one point that the basic property of these oxides are increasing because of increase in the metallic nature of their elements. Thereby, their oxides are becoming more and more basic down the group. This is regarding the properties of the oxides and their general formula. Then comes halides. Halides of the 15th group elements. So they form two types of halides, MX3, MX5. MX3 are called trihalides, MX5 are called pentahalides. And we know that nitrogen is not having d orbitals. Therefore, nitrogen cannot form pentahalide. So, nitrogen cannot form pentahalide because of the absence of d orbitals. Others can form pentahalides. So, two types of halides are there, trihalides of MX3 and pentahalides of MX5 we have. Let us now take trihalides. In the case of trihalides, except BiF3, which is ionic in nature, all remaining trihalides are predominantly covalent molecules. So all trihalides are covalent except BiF3, which is coming out to be ionic in nature. There is completely metallic fluoride you have, therefore it's ionic in nature. All trihalides except that of NCl3, NBr3, Ni3 are stable. Except these three, remaining are all completely stable there now. That is the reason is because these molecules are very low polarity of NX bond. They are very low polarity of NX bond. And there is a large size difference between N and N halogen. The large size difference is there between nitrogen and halogen, as we can see very low polarity of N and X bond. Therefore, these halides are not stable. Means in the nitrogen, only NF3 is a stable halide we have in the case of nitrogen trihalides. So among nitrogen trihalides, stability order is NCl3 is stable when compared to NCl3. NF3 is stable, NF3 is stable compared to NCl3, NBr3, Ni3 because the size of the halogen atom is gradually increasing here. When size of the atom increases here, we can see bond strength decreases. Thereby stability will be decreasing. Among all nitrogen halides, the only stable one is NF3 molecule. Among the halides, pentahalides are more covalent when compared to trihalides. Penta means they are having plus 5 oxidation state now, and tri will having plus 3 oxidation state we have now. When you are seeing the Fazan's rule states that if you have more higher state here like this plus 5 state or higher state, they are going to have more covalent character. So we can say that pentahalides have more covalent character, the direct consequence of Fazan's rules now. Then all halides undergo hydrolysis. Except NF3, all trihalides undergo hydrolysis with water. NF3 cannot be hydrolyzed due to the absence of d orbitals. It's under normal conditions, it cannot be hydrolyzed NF3, but under normal conditions, NF3 cannot be hydrolyzed because of the absence of d orbital. That is, neither nitrogen nor fluorine is having a vacant d orbitals in that. So under normal conditions only, NF3 cannot be hydrolyzed. Remaining all can be hydrolyzed. Then coming towards nitrogen preparations. So dinitrogen is produced commercially by fractional distillation of liquid air. Now we know that air mainly contains N2 and then O2. Main components of air are N2 and N2. And if you see the nitrogen, liquid nitrogen's boiling point is 77 and that of oxygen boiling point is 90. Implies that boiling point of oxygen is higher when compared to boiling point of nitrogen. Boiling point of oxygen is more when compared to boiling point of nitrogen. So, when we are distilling the liquid air, first of all, nitrogen distills off. It vaporizes first, leaving behind oxygen. That way we can separate nitrogen from oxygen in the liquid air. So, it's commercially prepared by fractional distillation of liquid air. And these are the boiling point differences we have. So, therefore, first of all, nitrogen vaporizes, leaving behind the oxygen. Other things are laboratory preparation methods we have. In the laboratory, nitrogen can be prepared by reacting ammonium chloride with sodium nitrite. Not nitrate, it's sodium nitrite we have. So ammonium chloride, sodium nitrite gives rise to N2 gas. Other byproducts are water and then NaCl we have. So in laboratory, N2 is prepared by the action of ammonium chloride with sodium nitrite we have. The next one. It's also prepared by thermal decomposition of ammonium dichromate. Thermal decomposition of ammonium dichromate we have. So ammonium dichromate on strong heating also decomposes and gives N2 gas plus water plus Cr2O3 we have. Second one is thermal decomposition of ammonium nitrate we have. And very, very pure N2 can be obtained by thermal decomposition of barium azide or sodium azide we have. Sodium azide or barium azide we have. Azide ions, they are M3 minus are called azide ions. And this N minus 3, they are called nitride ions. This is nitride ion. This is nitride ion. This is azide ion we have now. N3 minus ion. So by heating, that is thermal decomposition of barium or sodium azide will give us pure nitrogen gas there now. So barium azide on heating gives barium and nitrogen. Means elements are being produced from these two. We are going to get pure N2 gas. These are the preparations of nitrogen gas. Then reactions of nitrogen gas. It's a colorless, odorless, tasteless and non-toxic gas. So no color for this, no smell and taste, non-toxic gas we have. Two isotopes are N14 and N15 are two stable isotopes of nitrogen. Metals like lithium, magnesium have high affinity towards nitrogen and they react and form respective nitrates are being produced. So magnesium forms magnesium nitride, lithium forms lithium nitride also. And these nitrides, when you hydrolyze them, so for example, if you take magnesium nitride with water, it will give us ammonia gas. It forms magnesium hydroxide and then liberates ammonia gas there now. So lithium and magnesium have high affinity towards nitrogen and form nitrides. So Mg plus N2, magnesium nitrate, lithium plus N2, we have lithium nitrate then. So these are the reactions of nitrogen. Then other reactions of nitrogen, dinitrogen combines with hydrogen also in the presence of ion catalyst and molybdenum promoter. Regarding preparation of ammonia, it comes under Haber's process also. We can see preparation of ammonia done by Haber's process. There we use the elements N2H2 only, and here the catalyst used is iron oxide and promoter is molybdenum we have. So with these methods using, we can prepare ammonia in large scale process. It also combines with oxygen at high temperatures only to form nitric oxide. It also forms NO when it combines with oxygen gas. So N2 plus H2, ammonia we have, N2 plus O2 we have nitric oxide. This is happening at high temperature. Then finally the uses of dinitrogen is used in the manufacturing of ammonia, Haber's process we have, and we have a calcium cyanamide preparation. It's an important fertilizer. It is used as a fertilizer. So ammonia, preparation of ammonia, preparation of calcium cyanamide is a fertilizer there. And to provide inert atmosphere. So N2 is basically inert because of high bond enthalpy, inert atmosphere in metallurgical processes we have. In metallurgy, when you're preparing reactive metals, they may react with oxygen also. So to remove, they will be removing air. They will be placing completely N2 gas in the atmosphere. So to provide inert atmosphere in metallurgical processes. And liquid nitrogen, dinitrogen is used as a refrigerant in order to preserve biological materials and food items. Liquid nitrogen is also used as a refrigerant in order to preserve biological materials and food items. With this, we have done with the nitrogen uses. So, what you have learned today implies that we have seen electronic configuration of 15th group elements. We have seen their physical and chemical properties. And then we have studied anomalous properties of nitrogen. We learned hydrides of the group, and we have learned preparation properties of dinitrogen, means N2 gas. So we have seen configuration, we have seen physical and chemical properties of 15th group elements, anomalous properties of nitrogen, hydrides of elements, and we have seen preparation properties of nitrogen. This is a homework you can take down.